Equilibrium. Have you guys talked about this guy yet? The two-headed monster? Do you know what that means? You guys talked about that equilibrium arrow, right?
Be shy.
The problem is that represents a dynamic process, nothing static. A lot of times, well, and this is totally normal from all your earlier chemistry, we write that arrow there, right? We haven't really thought a lot about what that meant. But we take it to mean that, okay, there was the reactants, and then something happened, we mixed them, and then poof, we've got the products, and that's the end of the story. And really, that just represents while they're reacting, and then once it's done, it's done. But the truth of the matter is, the way the universe actually functions is most processes don't really quit, they don't shut down. There's a combination of reactants to form products, but then something else is going on at the same time. Because not all of the reactants will produce product. And you'll be left with some of the original side. And the reason that you don't end up getting a total reaction into products has a lot to do with the size of the molecules or the ions, the intermolecular attractions between the molecules and the ions. And that might keep enough of these floating loose, or alternatively, they might not have enough energy. All of them might not have enough energy to totally react. So this demo is to show the dynamic nature, the continuing nature of a reaction like that. And so what we're doing is we're going to represent the reactant side with this tank, and I've marked it similarly to that chemical equation. This is the product side. There's no products. We haven't started the reaction yet. We're going to start. We're going to represent reaction by two different size containers. And I'm just going to start pouring H2 and I2 molecules into there. That'll represent the collisions that have resulted in a reaction. And then they'll form the HI. Now the thing you got to remember is, once we start building up the number of HIs, those HI molecules in this system are going to impact each other occasionally. Because of the kinetic molecular theory. All the particles in a system are in motion and they're all moving. So they're going to start to hit each other. Well, it's only a matter of time in law of averages before there's enough HIs with enough minimum energy to overcome their mutual repulsion, bash into each other, and react. Well, what are they going to react into? They're going to react into another stable form of H and I. At first, all there is in the system are H's and I's. H2s and I2s. That's all that's in the system. So that's all that's going to be hitting each other. So they're the only things that are going to have a chance of reacting. But as I react some of these, I'll have less of these and more of these. So I'll have fewer reactions, collisions between these guys, because I'm reducing the numbers, because I'll be pouring them in, right? So that represents fewer molecules on this side, fewer impacts, fewer reactions. This side will start to increase, so you'll have more reactions. So what will happen is, at first it just goes one way, but after a while it'll start going backwards. And how does it reach an equilibrium? Because, as you'll see if you haven't seen already, a lot of systems will demonstrate that equilibrium property. You look at some of the properties of these systems and you go, no, nothing's changing. The mass of the solid isn't changing, the volume of liquid's not changing, the concentration's not changing. But you can do tests with radioactive isotopes and see that, yes, indeed, there is a motion of molecules from one form to the other form, but overall it stays the same. Hence, equilibrium. So we got, how do we explain that? That's what this demo is hopefully going to help you get a visual for.
Okay. So he's forward, I'm backwards.
Different size cups, because different intermolecular forces between the particles, so we're just going to take that, that they would react at different temperatures or different amounts, right? And so that's why the different size cups. So, notice I've marked the level in blue on my tank, and of course it's going to reduce. His level was 0 originally, and of course it's going to raise. And at first, what's going to happen is exactly what you expect. But eventually, something's going to change. Something's already starting to change. Can you quietly in your own mind start to make little predictions as to when this process will end? reaction, right?
No. Yeah, anyway. I now equilibrium at the rate. Keep awesome. And we'll stop. There. Equilibrium. Thanks, like I said. That was all.
So when do we quit?
We're just putting the same amount back in as it's taking out.
Say it again.
When you're putting the same amount of volume back in as it's taking out.
We weren't originally though, because you could see like,
Yeah.
my container's
His
way
was full,
bigger
mine was
and
empty.
his is littler.
But now,
Mine was full, his was empty. Now,
because now they're equal.
But they're not equal in level,
Oh, no,
right?
the volume you're putting back in.
So what is equal?
say it again, you're right in the money.
You're right there. The volumes aren't equal, right? We see that.
Yeah.
But what is now approaching equal? Equilibrium. What is actually approaching equal?
Putting back in.
And what are our little cups measuring?
That's not a
The
coincidence.
amount of reaction. That's the one.
That's not a coincidence. Keep going until the rate of the forward reaction equals the rate of the reverse reaction, and then it's even. Once those two even out, then this won't change, that won't change, that stays the same.
So if you could cover us up and not even look, and you were just looking at levels, you'd see no change. It would look static now. And that would be an equilibrium. But now you can see what's happening, and it's not static. It is very much still occurring back and forth. But the rates are now equal. So no change to the overall system now.
And it'll stay this way as long as the outside conditions remain the same. So the temperature doesn't change, we don't pour more water in, something happens so that somebody takes some of the water out of here, for example, or this container springs a leak or anything like that. So basically you're talking about a closed system that stays closed.
Notice that the volumes don't have to be equal. Equilibrium never says that the final system has to have equal reactants and products concentrations. That's not equilibrium. Equilibrium only defines the rates. Okay? It has nothing to do with what the end result is. Okay?
But we gotta shift it now.
Let's shift it. We did Le Chatelier's yesterday. You understand his principle? Let's increase the concentration of something. Let's make it the react.
Oh, a bunch of H2 and I2.
And what did we notice about the forward rate? Engel was putting his cup in as much as he could. It wasn't full anymore. It was full at the beginning, but as the collisions occurred, his cup level actually decreased to the point where it was the same as mine, and obviously mine is much smaller than his. So he had a system where his forward was as much as it could be. But now we filled up that reactant side again, his cup will probably fill up higher than mine again. So what should happen now to the system?
I've got way more H2s and I2s in my system, so there's more molecules, there's more collisions. Just by law of averages, because there's more of them in the system. More collisions, more chances that they'll react, so more reaction. And the forward reactivity rate goes up. See?
So what is going to be the sign that we're back to equilibrium? You have the advantage of actually seeing the reaction rate. You can't see a reaction rate on a molecular level. You see evidence of a reaction rate. You can't see it. Today you can. So how do you know we're at equilibrium? What will tell you?
Isn't the same thing, the forward reaction equals the reverse reaction?
Well, that would be this,
Yeah.
right? Which you could stop and say, please show us. And then you go, yeah, you're at equilibrium because the rates are the same. And I'd say, your theory, totally correct. But in actual practice, very difficult to observe. But what's easier to observe?
Levels.
The macroscopic properties of the system. The color, the concentration, the volume, etc.
How do those properties tell you we're at equilibrium? Because they won't be equal. I should say, they may be equal. In certain reactions, maybe the forward and reverse are the exact same size. And you will have 50% products and reactants. That's a chance.
Possible.
Not in our reaction. So how will you know that we're at equilibrium?
When the volume stops going up.
There you go. When these stop changing,
Right.
when it looks static, then officially these are probably the same because this isn't changing anymore. So have the volumes changed in a while?
In the last few trials, does that state about the same? What would you say? Or you weren't watching it? We can just keep going for a little bit, and then you can be watching that now. That will fill it for me. Right?
That works a lot better.
Pretty cool.
Okay. Notice the change in the levels, right? We added a lot of reactant. what happened to the system? The product concentration ended up going up, right? And that's the shift that we would see. We would see the shift to the ACE shift, and it would shift to products, and the concentration of products went up.